We will explore geometric series and a few of their applications. This might be the topic you would have seen in high school about the summations, where the terms always differ by some factor. So for example, here you notice that to go from the first term to the next, we multiply by 3. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27, and so on. What the question is at the end is, what is the total sum? Whether or not the sum ends is going to be the two cases that we will consider. Now, in this case, it's actually fairly easy to see that the sum will not come up to any particular number because we're adding numbers every time they get bigger and bigger and bigger. If we add infinitely many numbers that continue to increase, then we will never be able to get to a finite result. So the answer here is infinity. On the other hand, if we're dealing with fractions, we can't make the same argument about the final summation. So notice here we also have geometric series, except for we are multiplying each term by 1/2 to get to the next one. 1/2 times a half is a quarter. 1/4 times a half is 1/8. 1/8 times a half is 1/16, and so on. Now here, every consecutive term gets smaller and smaller and smaller. So is it possible to say that the sum is equal to something because we keep adding things, but the things we're adding are getting infinitely small, so maybe at some point they're not going to make a real contribution anymore? This is what the study of geometric series is about, figuring out what the total sum is going to be in either of these cases. Most standard way, the geometric series, which is just another way to say sum, can be written as 1 plus r squared plus r cubed, and so on, where r stands for ratio, and that is the common number that you multiply each term to get the next one. Now, this is a standard way to write this down, and you notice that the first sum we considered here matches this, whereas the second starts at 1/2, so it doesn't quite match our summation here exactly. What we can do to make this happen is take this entire sum and factor out 1/2 out of it. Factoring out the common ratio or the first term will keep the common ratio intact, so will not affect the rest of your sum. We will see how we can deal with that kind of scenario later. For now, what I would like to do is think about, if I have such a sum, what can it possibly equal to? And one of the ways to consider this argument is to draw what we have corresponding to our summations. On the one hand, I have this line, which is y equals x. And on the other hand, I'm going to have this line, which is actually y equals rx plus 1. It's not yet clear why I need both of those lines, but let's take a look closer here. If I start at the origin and I walk up, let's say this is my unit of 1. This is a distance of 1. Then if I move to the actual diagonal line, the horizontal distance is equal to the vertical one. So my horizontal distance here will also be just 1. If I start here now and I go up to my line vertically, I notice that this line has a slope of r, which means that to go from one point on this line to another point on this line, my rise over run has to equal to r. Here I'm going to rise this much and run 1. So my rise over the run, which is equal to 1, has to equal to r, which means my rise has to equal to r. And again, going to the diagonal means that I am going to produce the same horizontal as the vertical shift. So this part is going to be r as well. We can repeat the exact same argument. Let me zoom in here so that it's easier to see on each consecutive step. So what I'm going to do now is move up to my line here and think about what is the new distance. Again, because I'm on a line of slope r, I have to have rise over run equals to r. So in this case, I have rise over run, but now my run is r, equals to my slope r. which means that my rise has to equal r squared. So this is going to be r squared, and so on. So what you notice is that this geometric series actually models the height between the origin and this point of intersection of the two lines. Notice that what I'm adding is 1 plus r squared, and if I continue, I'm going to get more and more terms in this summation. So what I would really like to know is if I'm adding them all up, where am I going to end up? Well, if I'm adding all of these guys up, I'm going to end up at this point of intersection. And now, this is what I have to solve for. What are the coordinates of the point of intersection? Now, the points of intersection, to compute the coordinates, I simply have to set the two equations of the lines that form said point of intersection to be equal to each other. So I have rx plus 1, which is my first line here, equals to x, which is my second line here. If I solve this equation, I'm going to skip a few algebraic steps here. What I'm going to find is that x is equal to 1 over 1 minus r, and then y, by extension, has to equal to the exact same number because this point lies on the line y equals x. So whatever x is, the y coordinate has to be the same. And that's also clear because, look, the vertical distance between the origin and this point is the same as the horizontal distance. I can also see the geometric series appear as the horizontal displacements on this path of mine. So y is also equal to 1 over 1 minus r. That means that vertically, from here to here, by adding up these pieces, which correspond to my geometric series, I ended up at 1 over 1 minus r. And that is, in fact, my total sum of these geometric series. One thing to note is that this formula only holds if r is less than 1. If r is less than 1, then the slope of this line is less than 1, which is the slope of this line, which means that this line is going to be less steep and a point of intersection will actually be produced. If r is bigger than 1, my top line will be steeper than y equals x, and the two lines will actually never intersect. So this only works for r between 0 and 1. Notice that we're only going to be considering the cases when r is bigger than 0, so we're stating this formula with that as the condition. Now, this formula in general describes what happens to the summations, the geometric sums, that are infinite. So they go on forever, and we notice that they have a concrete finite number as the total sum only if the ratio r is less than 1, so a fraction, really. What happens to the sums that have an ending point, the finite geometric series? In this case, we're going to use an algebraic method to derive the formula just to see the variety of methods. Last time we used something geometric with the lines. This time we're going to ask algebra for help. We're going to let this sum be called S, and then think about what does it mean if I multiply r to the front of it. So that means that for rs, I have taken this entire sum and I multiplied it by r at the beginning. What's going to happen if I open up the brackets? Well, r will get multiplied by every term on the inside up until the last one. So r times 1 is going to be r. I'm going to align my bottom sum so that if I get equal terms, they're actually aligned to each other. R times 1 is r. What about the next term? R times r is r squared, so plus r squared. R times r squared is r cubed, and so on, all the way up to r times rn, which will produce an extra term on the end. So take a look at this formula and really persuade yourself that this is in fact this entire summation multiplied by r at the front. What we're going to do next is, because we notice that a bunch of these terms are the same, we're simply going to subtract the two sums from each other. So I'm going to consider S minus RS, and I'm going to subtract in a column the way that we normally do with large numbers or large expressions. So what are we going to have? I have 1 minus nothing, so that's a 1. And then I have r minus r, so these guys will cancel each other out. R squared minus r squared, all the way down, these terms will cancel each other out. Except this last guy that doesn't have a corresponding term at the top. So here I have nothing to match it minus this term, which means that altogether I will end up with a negative of this last term. This is what I have on the right-hand side of this equality. What about the left-hand side? Well, the left-hand side was S minus RS. So let me write down in a bit more of a compact form what I have here to be able to solve for it. So we have derived that S minus RS is equal to 1 minus r to power n plus 1. The idea was to be able to say what this summation is. So really, I'm after the value of S. So I would like to solve this expression for S. I can factor S out on the left-hand side, and I'm going to get 1 minus r as whatever is remaining in the brackets. And once I have that, I simply divide both sides by 1 minus r and get 1 minus r to power n plus 1 divided by 1 minus r. And that is the final formula for the finite geometric series. Let's see how we can apply this. So for example, here is the geometric series, 1, 2, 2 squared, 2 cubed, and so on, all the way to 2 to power 10, added up together. One thing you have to figure out right away is what is in fact your value for r. So the value for r here is the constant factor, the way that you get from one term to the next. And here I can notice that what we do is multiply by 2 every time. So for this particular summation, r is equal to 2. The other thing present in the formula is n. Let's look at what the sum actually was. First of all, noticing that I actually do match 1 for 1 as the first term. And n is the last power of the common ratio that is present in the sum. So in this case, it's equal to 10. With r equals 2 and n equals 10, again, noticing that my first term is a 1, I can now simply plug everything into this formula. R equals 2 goes in, n equals 10 goes in, and altogether I'm going to have 1 minus 2 to power 11, because I have n plus 1, over 1 minus 2. Now, of course, I can simplify this expression a little bit, especially because on the bottom I have something fairly simple looking. So altogether, I will have 2 to power 11 minus 1. If I compute that as negative 1 and then negate everything on the bottom to accommodate for that answer. This formula is going to come in very handy when we're doing a variety of our simplifications. However, I would like to point out now, as I will point out later, is that you got to make sure that your actual series starts at 1 in order to be able to apply this formula. Let's just look at the summary of what happens to the geometric series that are, once again, infinite, as the number of terms, in fact, tends to infinity. We have two cases, and for one of them we derive the formula, but I would like to bring it all together to have one big picture in mind. So my series here are 1 plus r squared plus r cubed, and so on. They go on forever. If the ratio, this r, is bigger than 1, that means that every consecutive term is bigger than the previous one, and I am adding bigger and bigger and bigger numbers, which means that altogether, there's no way I'm ever going to end up with anything finite, and the whole thing tends to infinity. If my ratio is small, in particular, if the absolute value is less than 1, and I've already mentioned we're actually only going to consider r greater than 0, so for us, this really just means between 0 and 1, what I have is adding smaller and smaller and smaller numbers, because fraction raised to higher and higher power, remembering the dominating power analysis, will produce smaller and smaller numbers. And we've derived a formula for that stated that this entire sum is going to equal to 1 over 1 minus r. There's a really nice, very concrete visual that we can use to justify how adding infinitely many terms can end up with a finite number. So what we're going to do is take a look at the series we've actually already seen: 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. So if this sum goes on forever, what does that equal to? If I simply plug in the formula, I can of course calculate the number, but I'm going to do it in a slightly different way this time before we convert to using algebra at all times. Let's say I have a square here, and I have a square of side length 1. So the area of the square is 1 times 1, overall 1. I would like to, inside this square, be able to construct this sum. So first I notice that I need 1/2. Well, if the entire square is 1, then 1/2 of the square is in fact a half of the square. So I can just mark off a half. This is my half, so I will be counting this as the part of my summation here. This area corresponds to this term. But then I'm adding up a quarter. Well, a quarter is a half of a half, right? And the half, well, maybe let me write this down. Quarter is a half of a half. What I haven't accounted for yet is this half, so I can now take a half of that. So I can split this into 2. This is a quarter, and if I'm adding it to my calculations of the area, the addition here now covers both of these pieces. What about 1/8? Well, conveniently enough, 1/8 is a half of a quarter. What I have unaccounted for so far is a quarter. A half of that will be 1/8. So I can cut that in half. This is my 1/8, and I shade that in. So the shaded portion so far is my sum, 1/2 plus 1/4 plus 1/8. Notice how I can continue going. Every single time what I do is take the area that I have not yet covered, divide it into 2, and shade half of it. This next area will correspond to 1/16. If I do it again, half, shade it, this will correspond to 1/32. Half, shade it, 1/64. If I keep going forever, I will simply end up shading the entire square. It's clear I'm never going to be able to escape the square, so my sum can never be bigger than the total area, which is 1. But it's also clear that as the infinite process, I simply walk myself over, shading the entirety of the square. So the total sum here, the total area covered by this process, is in fact equal to 1. And you can make these kinds of geometric arguments for lots of different geometric series with different ratios. For example, if I take 1/4 plus 1/16 plus 1/64 and so on, so my common ratio here is going to be 1/4, I can create a picture similar to this first one to justify why the area is equal to what it is. So here I start with a quarter, so I'm going to divide my square into fourths, thinking about the actual meaning of fractions. 1/4 means 1 part of the 4. Now I have 4 parts. I'm going to shade one of them. This is going to be my 1/4. For the next term, I have 1/16. So in a similar fashion as before, 1/16 is a quarter of a quarter. So I have this repetitious process happening again. I'm going to pick one of the quarters, like this one here, divide it into 4, and shade 1/4 of it, which overall ends up being 1/16. 1/64 is a quarter of 1/16. So I'm going to simply repeat this process in the next available little square. 1/64 and so on. So now, again, it's clear that I'm never going to be able to escape the square because I just keep drawing smaller and smaller squares here. But what is the total shaded area? For this one, you might have to squint a little bit and just step back a bit. Notice that what I have is this structure here of the squares that I'm going to be shading, but these squares also repeat in the middle like this and in the bottom like this. So what I have is this exact same structure 3 times within this big square, which means that what I'm shading overall is one of the 3 pieces, so total of 1/3. And that's exactly what we're going to see if we plug this series and use our formula. Now, geometric understanding of this series is really helpful for when it comes to word problems and really understanding the concept of this series. What we're going to do next is practice a little bit with computing them algebraically. So we have 2 cases for geometric series, and these are their formulas. The infinite geometric series that go on forever, only what we call converge or have a finite sum, again, if r is between 0 and 1, in more generality between -1 and 1, but we will keep to the positive cases, and the finite case where the sum stops at some value of r has this general formula. Let's see how we can apply them. So first of all, we have to figure out if the given series is actually geometric or not, which means we have to figure out if every consecutive term can be obtained by some constant multiplying of the previous term. 1 times 1/4 is a quarter, 1/4 times 1/4 is 1/16, and so on. So we can see that this is in fact a geometric series or geometric summation with r equals 1/4. In fact, this is the exact same one, except for the +1, as we've considered on the previous page. Now, once we figure out that they are geometric series, we have to figure out, are they infinite? So we have to apply one of the formulas, or finite, so we have to apply the other. This goes on forever, which means that we will have to apply ours. We're now checking the condition to see whether r is less than 1, and therefore whether or not the summation will have a finite number. The r in this case, the value for r is 1/4, so yes, this falls under this case, and we can plug this into here. The last thing we have to check is to make sure that the formula actually matches up. Notice that both of these formulas are for geometric series that start with 1 and proceed to half powers of the fixed ratio. This sum does start at 1, so it matches this formula 1 for 1, and therefore we can simply plug it in. So we have 1 over 1 minus r, which is 1/4, therefore 1 over 3/4, and altogether 4/3. Notice that this is consistent with what we've gotten on the last slide. 1 plus this entire sum ended up being 4/3. This entire sum without the 1 ended up being 1/3, which is the exact same outcome. Let's take a look at the next summation here. We have 4 cubed, 4 to the 4th, all the way down to 4 to power 50. So first of all, it is finite, so we're going to have to apply this formula if anything at all. But what we notice is that it doesn't start at 1. So we're going to have to do some adjusting before or after applying the formula. Knowing that the next example is similar, I'm going to apply one technique to this number 2 and a different technique to number 3. The technique that I'm going to apply to this first one is to factor out 4 cubed. If I take out the first term, then that will become 1, and then consecutively, I'm going to factor out 4 cubed from everything else. If I factor out 4 cubed from 4 to power 4, I'm going to get a 4. The next term is going to have a power 1 up, so 4 squared, all the way up to me taking out 4 cubed from 4 to power 50, so 4 to power 47. Now, this matches the formula exactly. We have 1 as the first term, we have the ratio as 4, and we have that the end value, being the highest power here, is in fact 47. So I can apply the formula for the finite geometric series onto the summation in the brackets. 4 cubed is going to have to be multiplied separately afterwards. So I have 4 cubed times, and now this formula for the specified values of r and n. So 1 minus 4 to power 48 divided by 1 minus 4. You can, of course, simplify this expression I'm going to leave it as is just to be able to see the actual structure of the answer here. Now, as I already mentioned, this next one looks very similar. We have a finite number of terms and we have a fixed ratio. So this is a geometric series, a finite geometric series, but we're faced with the same issue as above, where the first term is not a 1. I can do the exact same thing here and factor out 4/3, or I can apply the formula directly, but recognize which terms I am overcounting. The formula, as written, would be applicable if my series started at 1, which means that if I do apply the formula, this is the one I will have to subtract to, in fact, even things out. So what I do have here is then r is equal to 1/4 and n is equal to 9, as we can see for the power of Rn. So my overall result is going to be plugging those values for R and N into my formula. 1 minus 1/4 to power 10 divided by 1 minus 1/4 minus that one term that I overcounted for. So again, remember that the formula will calculate everything from 1 on, but what I have is only this chunk of the summations. This one needs not to be counted, so I'm going to have to subtract it out. And there we go. I encourage you in both of these scenarios to try the other method. So for this scenario, to try the method of actually applying the formula all the way and then recognizing which terms in the beginning you're overcounting by. And in the third case here, to factor out what you need and then apply the formula directly. This will really help for you to recognize which method you prefer. Now for this last one here, so what I notice is that I don't start at 1, but I do have a common factor. Everything gets multiplied by 3. This is an infinite series, so the numbers will grow bigger and bigger and bigger. My R value here will be 3, which means that if I do have an infinite series and R is bigger than 3, this summation will not have a finite outcome and will in fact tend toward infinity. Now on WebWork, there's a bunch of exercises that will get you more comfortable with the summations. This is something that requires quite a bit of practice, so be patient and do exercise as you go along. What we're going to consider next is an application of the geometric series to the branching structure of lungs. In order to better understand it, first watch the video that is linked to in the comments to this lecture. What we've learned is that our lungs basically look like trees, with one main trunk coming down from the throat, separating into 2 bronchi that each continue to separate further and further into smaller and smaller bronchioli, at the ends of which are air sacs called alveoli. Now, what we would like to do, for example, is not only be able to count the number of separate tubes that this creates, but also count the total surface area of the lung or the total volume of these tubes or anything really related to them. So let's assign some mathematical notation and see how this connects to what we've discussed earlier. The main tube here, the trachea, we're going to call generation 0 because it's just one tube. This is where it all starts. And then for each following generation, we're going to call it depending on how far away it is from the first generation. So this is generation 0. Generation 1 are going to be the bronchi that lead into the left and right lung. And then when they split even further, this is now at level 2, generation 2. So for each generation, you're thinking sort of cross-cut. What we are going to assume is that each branch, no matter what level it's at, splits into some fixed number of what we will call daughter branches. So we are going to assume that each one splits into B for most generality. For some B, what I have in the picture is always 2. Each branch always splits into 2, but that need not be the case. And what I'm going to also label is the number of branches for the generation n. So for generation 0, for example, x0, the number of branches is simply 1 in our case, or more generally xn. For generation 1, let's think in most generality, not just as on the picture here. Whatever number of branches I had, it will be split into b daughter branches. So the next generation will have b times x naught. For the following generation, I'm going to have b times the previous generation. Again, recognize that each generation we're going to have one branch split into b branches. Now here, I have b times the previous generation, but my previous generation can also be written out as in terms of x naught. So this x1, I will be able to plug in from earlier and replace with b x naught. So I'm going to altogether create an expression that only depends on b and x naught. Combining the two b's together, I see that I get b squared x naught. What are we going to have in the third step? Well, the same pattern repeats. No matter what generation I'm at, the number of daughter branches will be always b times the previous generation. And the previous generation has already been expanded to be written in terms of x naught, so I'm going to simply replace x2 here by the expression 4x2 that I've just derived from earlier. So b squared x naught, and I'm going to have b cubed x naught. And this, of course, will continue on for as long as we wish to compute this for, and I can derive the general formula for xn, the number of branches in generation n, as b times the number of branches in the generation n minus 1. And then following the pattern here, I notice that in each generation, the power on b increases. So I will have altogether b to the power of n x naught for the total number of branches in generation n. Now, this is then the rule linking generations. For lungs, the structure really isn't this uniform. There is not always the exact same number of branches that each branch splits into. In fact, this differs between the left and the right lung because the left lung has to also fit the heart and therefore is generally smaller altogether. What we do know is that on average, for lungs, we can assume that this b value is going to be 1.7. Now, this is on average. This is the average number of splits. Notice that, of course, no branch splits into 1.7 other branches. That's not possible. But along altogether through the lung, this is the average number that we can assume for the b value. Then what we have in terms of the rule linking the original number of branches, which in our case for lungs is 1, and the number in the nth generation is x sub n is going to be b, which is 1.7, to power n times x naught, which is just 1. Therefore, our formula for the nth generation for lungs is really quite simple. The other question that we can ask not only is how many branches are there in the nth generation, but rather how many branch segments are there all together by the time we get to a certain generation. In lungs, we know that the number of average generations in an average human's lung is about 20. So let's think about how we can approach that question. If we start with one branch, how many branch segments will we have in 20 generations? Now, this of course means that we will have to add up the number of branches from every generation up to 20. So what do we have altogether? Well, first of all, this is our general formula. The first real generation is what we call generation 0. So the number of branches there was x naught. The generation 1 had x1 number of branches, generation 2 had x2, all the way up to x19 for the total number of generations of 20. What do we have in our case if we substitute our formula? Well, we know we started with 1 first branch, so this is our value for x naught, and then the rest of them follow this formula as well. Notice that this formula holds for x naught as well. If I plug in 0, 1.7 to the power 0 is simply 1. So for the first 0th generation, I have 1 branch. The next one, I have 1.7. Then I have 1.7 squared, all the way up to 1.7 to the power 19. And this we can easily recognize as a finite geometric series. Now, the great thing about that, of course, is that we already have the formula to how to compute the total number of this summation. We notice here that it doesn't, the R value, your 1.7, in our case we also called it B, because it's finite, doesn't have to be below 1. We can apply that formula anywhere, and the formula altogether is 1 minus 1.7 to the power of n plus 1, so to the power of 20, divided by 1 minus 1.7. If you compute this number, this turns out to be just above 34,150 branches. So this means that by the time we get to the alveoli air sacs, our lungs have constructed over 34,000 branch segments. That's a big number for human body to contain. And in fact, alveoli themselves are even more impressive because, as you recall from the video, this is what each bronchiole ends with, a sac of alveoli. The surface area of these guys, which is exactly what accommodates gas exchange of turning and exchanging oxygen and carbon dioxide, if these guys are turned over and spread out, their overall surface area actually approximately equals to the area of a tennis court for an average person, which is incredible. Our bodies have learned to fit very complex system into very compact packages. This problem can be similarly extended for computations not only of the number of segments of the branches, but also, for example, of the total volume of the branches and the total surface area. The book goes through these examples in fairly detailed way. I'm going to simply sketch how you would approach it. So the one thing that we notice from above is that because each one of these branch segments is of a pretty standard cylinder shape, we can use that to our advantage. So for the cylinder, we're going to then need the radius and the length. Now, at every generation, the radius and the length are going to be different. The bronchiolae are getting smaller and smaller and smaller, so I'm going to label the radius at nth generation as Rn and the length at the nth generation as Ln. And these two measurements follow similar rules as the number of branches did all along. So we can similarly derive the fact that on the nth generation, the length is actually 0.9 to power n of L naught. So every time we split into a new generation, the length becomes 90% of the previous generation's length. And the radius is always 80% of the previous radius length. In order to calculate the total volume, we first have to calculate the volume of the nth branch itself. Now, in this case, because it is just a cylinder, we already know what a volume of the volume of the cylinder is. It's pi r squared times the height of the cylinder, or in this case, the length. So it's going to be pi rn squared times the length. And now I can submit the actual values in terms of n and the very first 0th generation length and radius, which we can easily measure, into this formula. What am I going to have? I'm going to have 0.8 n r naught all squared times 0.9 n L naught. Now, in order for me to calculate the total volume of all the branches up until a certain generation, so let's say generation 20 like we've done before, of all branches up to 20 generations, all I have to do is then set up a summation where my value of n goes similarly to this expression from 0 to 19. So what I'm going to have is the sum where n goes from the 0th generation to the 19th generation of this value. Okay, so if I want to label this, for example, Vn, I can, or I can simply rewrite the whole thing. So 0.8n R naught squared, 0.9n L naught. If you simplify this a little bit, you will notice that this is, again, nothing else but a geometric series. The only things that depend on n here are these two values. R naught and L naught are in fact constants, so they can be taken out of the summation, and then you will have just a geometric series on 0.8 and 0.9. Applying the formula, we can see that this is approximately equal to 1510 centimeters cubed for an average human lung. Similarly, we can calculate total surface area, and in fact, we don't even have to set up anything new, and that is because the surface area of the branches can be also calculated using this cylindrical structure, and that's going to be the sum, again, if you wish, of the first 20 generations of the surface area of each cylinder. And the surface area of each cylinder is 2 pi r L. Okay, and if we expand it out just like we did here by plugging this in and then massaging the sum a little bit, we'll be able to apply the geometric series formula and calculate this number. If you're interested in how these calculations work out, first of all, I encourage you to try this for yourself. And secondly, the textbook goes through all the details of the actual calculations, so you can look it up there. What we're going to talk about in the next chapter is how to take these branching structures and study them in a different kind of way. We will see how gas exchange can be modeled using something similar, as well as other processes in the human body and in nature.